This one here from the acid-base work booklet. All right. All right. So the rules are, when you write out the ionic equation of this, you have to think about, are the substances solids, aqueuses, that kind of stuff? Are the acids strong or weak? Right? Those are the main things that you need to think about. So when you see hydrochloric acid, you're thinking, is that strong or weak? Strong. Okay? And this is a sodium carbonate solution, so that's an aqueous solution. So if it's a strong acid, it's going to fully ionize, and so therefore it's going to be a H plus. Oh, this is Bronsted-Lowry. All right. So you would have to show that it is going to hydrolyze. You may not actually have to show that this is going to hydrolyze, but the idea is that you understand that this occurs prior to the reaction occurring. Okay? So that first reaction of the hydrolysis of the hydrogen chloride occurs before that reaction with the sodium carbonate. So within the hydrochloric acid, that reaction has already occurred and it's produced H3O plus ions, and the H3O plus ions are the ones that's going to react with the sodium carbonate. Now also, you need to recognize that the ionic equation is the most accurate representation of what's occurring in the beaker in the reaction. All right, so whenever you think about, do I need to add this or do I not need to add this? You need to think about what's occurring inside the beaker and then to make a decision on that. So the H3O plus is added to sodium carbonate solution. So that sodium carbonate solution is made up of Na plus ions and CO3 2 minus ions, right? Because it's a solution, they're not stuck together. You should hopefully remember that sodium doesn't do much in reactions, or the sodium ion doesn't do much. So therefore it's just plus the CO3 2 minus. Okay, and then because it's a strong acid, it's a single arrow, you would have that reaction where the acid plus the base makes the carbon dioxide and the water and the salt. So this is going to form water and carbon dioxide. And the salt that would be produced, the Na plus and the Cl minus, are both spectator ions, so I'm not going to add those in. Okay, I need to balance this equation, so I need a 3 here, a 2 here, and that's it. All right? So that's a balanced equation for that one there. All right? Yeah?
Do you not split up the HCl? Do you keep it together for the first step?
So in the first one, you keep it together because you're showing the hydrolysis effect of HCl. To make HCl, there are lots of different ways, but in theory, what you're doing is you're adding hydrogen chloride to the solution, and then hydrogen chloride gas would split apart in that way. So that's not technically the way you make HCl industrially, but in theory, that's what it would be. So that's why you keep the HCl as a molecule in that first equation, right? Yeah?
For the second one, I'm not sure, why is it CO3 and then there's no salt form?
Okay, so happy with the idea that the CO3 comes from the sodium carbonate solution. Happy with the idea that the sodium carbonate solution would have already had these two split. Yeah? So if these two have already split, you've got a beaker full of these and a beaker full of these, and these do nothing, and these do something. So therefore, they are shown in the ionic equation. So why don't you show the salt formed at the end? Because when you put these two beakers together, the sodium ions just kind of flow into the other beaker and do nothing. The chloride ions, which are also in the other beaker, in that first beaker, sit around and do nothing as well. So they just not included in the equation. So this is me showing that, I don't have to write out the full thing and then cancel out stuff. I could just cancel it out in my head. Yeah, cool. So let's then show what happens when you do the solid lithium oxide and the phosphoric acid, right? So the phosphoric acid, is that a strong or weak acid? Weak. Which means that the majority of those phosphoric acid molecules will be in molecule form. So when you do an ionic equation, you have to show it as a molecule form. So instead of splitting that up in a hydrolysis equation, but you still need to know how to do a hydrolysis equation of it, you would just show the H3PO4 as an aqueous, and this would be part of your ionic equation. Solid lithium oxide, so because it's a solid, it stays together, so it's lithium oxide solid, right? It's a weak acid, so you got to do the double arrows. And then you need to be able to do this, and it's going to form water, and it's going to form... Now, when you add the acid to the thing, you're going to make a salt, and you have to find out if lithium phosphate dissolves in solution, which it does not, right? So therefore, it's lithium phosphate ions. Oops, I don't need those. Okay, so lithium phosphate will precipitate, so it stays as a solid. Okay, so that's actually the full ionic equation, because everything reacted and everything in theory changed states in somehow.
So there's no hydrolysis.
So for a weak acid, you need to know how to do a hydrolysis reaction of it, but you do not need to show it, because in theory, it doesn't occur to a large extent in the original beaker of phosphoric acid. So in the original beaker of hydrochloric acid, this occurred to a large extent. In the original beaker of phosphoric acid, that reaction did not occur to a large extent, so therefore the majority of it will be this. All right, let's do the... Let's change this up and let's just move on. Okay, so weak acid, don't put them into the thing, all right? Or don't do a hydrolysis equation for it. Treat them as an individual thing, all right? Let's go and do this next one, actually, this last one, potassium metal and sulfuric acid. So sulfuric acid is a strong or weak? Strong, so you can show the hydrolysis reaction of it, because this will be occurring in significant amounts, right? Actually, yep, single arrow. HSO4 minus, because it's only reducing once, and there, that makes the H3O plus. Then the H3O plus AQ is added to potassium metal. So whenever you have it adding to a metal, you need to remember that it's not a charged substance, and it's just a solid, right? It's going to occur to a large extent, form H2 and H2O and K plus ions. Where did that H2O come from? Where did this H2O come from? It's from the idea that this H3O plus is donating a proton, and whatever's left is still there, so therefore it's still the water there. This H3O plus is donating a proton, turning it into water, right? To balance this equation, I would need to do a 2 there and a 2 here, right? Technically, to balance this equation, I also need to balance out charge, and you'll learn this about this in the next topic of redox. You would also need to put a 2 here and a 2 here to balance out the charges. But we'll talk about that when we get to redox. All right? So that's the ionic equation that occurs for that one, except I haven't put in states in there. Also, you should check that potassium sulfate doesn't precipitate, which it doesn't. All right? So potassium sulfate, which would be the salt that's produced, is not insoluble, so therefore it is aqueous. Now, we have to take those rules again to when we do ammonia and ammonium, right? However, you've got to recognize that ammonium chloride solution is simultaneously an ionic substance as well as an acid. So the ammonium chloride sits inside the beaker as NH4 plus and Cl minus. So it's already dissociated within that beaker, and because it's dissociated within that beaker, we need to show it as separate to each other. So the idea is that you don't split weak acids, but ammonium chloride or ammonium nitrate or whatever ammonium chloride is not a weak acid. I mean, it is acidic, but it is not, the full thing is not an acid. It's only this portion that is acidic. And because it's only that portion that is acidic, that's the portion that gets put into the ionic equation. So it's a bit tricky. Weak acids, you don't split apart, but it's the weak acid component that doesn't get split apart in ammonium chloride. Therefore, you can split apart the ammonium chloride into its component parts and then just say the ammonium ion is the part that reacts. So let's do this ammonium chloride with solid sodium carbonate. So because it's a weak acid, we do not split it apart. So we wouldn't split like the NH3 and the H plus apart. Plus a solid sodium carbonate. So Na2CO3 solid, right? This would react to form water, carbon dioxide, a salt, which is the Na plus part of it, and ammonia, because that's this hydrogen here on the NH4 is going to give up its hydrogen to make the water, and what's going to be left here is the NH3. All right, so to balance that equation, you would need to double this, double this, double this, double that, and that's it. All right, so add in a few states, and there's your ionic equation. Okay, and that's going to be aqueous because it's being done in a solution. Okay, right, so even though the ammonium chloride is a weak acid, it's the ammonium part which is the weak acid, which doesn't get split, so the chloride can be split from it, right? That's that one there. Does that clear that one up a bit? Do you want to have a look at the ammonia solution in hydrochloric acid? Yeah, so the hydrochloric acid does undergo hydrolysis. So therefore it forms H3O plus Cl minus. So that's the hydrolysis equation just for the hydrochloric acid. So the H3O plus reacts with the ammonia, and that's a solution, so it's AQ. And it turns into NH4 plus H2O, AQ, and liquid. Okay, so strong acid with that weak base does form that. Thomas, you want a question? No? Okay. All right, let's find an ammonia with a weak acid. Here we go. So ammonia solution with phosphoric acid is a weak acid and a weak base. So the phosphoric acid, it doesn't get split up. The ammonia solution doesn't get split up. Well, it wouldn't be because it's the base, right? Double arrow because it's a weak stuff, right? Then you have your H2PO4 because it's donated 1 proton, and NH4 plus AQ. And that's the ionic equation for what's occurring there. Right? Okay, that's it.